Hello everyone and welcome to this presentation, which is all to do with first year integration. So this is still under the umbrella of calculus. So we've already done some work on differentiation. It's now time to do some work on integration. And as it says here for your notebooks, integration is the inverse function to differentiation. So let me explain what that means. So here is an equation, y equals 2x cubed minus x to the power of 4. If I differentiate that equation, I will end up with a gradient function, which is dy by dx equals 6x squared minus 4x cubed. So we've been working with these gradient functions for a long time now on the previous presentations. And what I'm here today to tell you is that if I reverse that process, if I start with a gradient function and want to get back to the original function, then that method that we would use is called integration. And similarly, with differentiation, there is specific notation used for differentiation. The same can be said for integration as well. And this is the notation that we would use. So this sort of elongated S shape is the integration side. So what we would be saying here is that I'm going to integrate 6x squared minus 4x cubed with respect to x. That's what this dx means. And as far as you're concerned, with respect to x basically means I'm going to integrate this polynomial that has lots of x's in it. And we now know the answer to this question will be 2x cubed minus x to the power of 4 based on what we can see in the diagram above. Okay, so let's investigate that a little bit in more detail. So as I've just said, this symbol here is the integration symbol, and this can be written down, of course, in your notebooks. This symbol here means that I am integrating with respect to x. It is the variable that I am using in my integration. So dx means that I will be integrating a polynomial that has x's in it. And here is my answer of 2x cubed minus x to the power of 4. But that's not quite the end of the story. And so we have to be a little bit careful when we're integrating as opposed to when we're differentiating. Because remember, if I had a constant on the end of this answer, if I was to differentiate that constant, it would disappear to 0. So when I am reversing the process and I am integrating, I need to put that constant of integration back in again. So in every question that I do, I will have a constant of integration. There are a few special cases which we'll talk about in the next presentation, but for general integration like this, when I integrate a polynomial and I achieve my answer, I must remember to put my constant of integration in at the end. Now, if you don't quite understand what I mean by that, think about what would happen if I differentiated the right-hand side. In theory, if I differentiate that answer, the right-hand side, I should get back to 6x squared minus 4x cubed. So the 2x cubed differentiates to the 6x squared that I need. The minus x to the power of 4 differentiates to the minus 4x cubed that I need. And then this plus c, which I might have to find, or I might just leave it as plus c, would differentiate to 0 using the skills that I learnt in the last presentation. So I need that plus c because when I differentiate it, I will get 0, which is represented in the left-hand side. And this value for c that I must make sure I include in all my integrations is called the constant of integration. Okay, so what I'd like you to do, please, I haven't taught you any of the rules yet for integration, but I just want you to investigate and see if you can work some of these rules out yourself. I'm going to give you 4 or 5 expressions, and what I'd like you to do either on whiteboards or on a piece of paper is I would like you to decide or try and decide what the answer to these integrals would be. So have a think, have a play around, write something down, see if it works. I would like you to integrate for me 3x squared. And you can, of course, decide whether you have the right answer or not, because in theory, whatever answer you decide is the right one, if you differentiate it, you should end up going back to 3x squared. So have a think, what expression would differentiate to give you 3x squared? Whatever that is the answer to the integral of 3x squared. Okay, now if you've had a go at that and you are correct, then you should have an answer of x cubed. Now again, don't forget the plus c for reasons we mentioned on the previous slide, but x cubed is our answer because if I differentiate x cubed, I get 3x squared, which is exactly what I need. So well done if you got that first one right. Here's the second, have a go at this one. So what expression would differentiate to give 10x to the power of 4? Okay, and if you've done that right, then you should find you get an answer of 2x to the power of 5, and then don't forget the constant of integration again. And to check that, remember, if I differentiate the 2x to the power of 5, I do indeed get back to 10x to the power of 4. Is there any patterns that you're starting to see when you perform these integrals? Number 3. Of course, by all means, pause these as we're doing them. Give yourself as much time as you need. But what is the integral of 8x with respect to x? What expression would differentiate to give 8x? And if you've done that correctly, you should end up with 4x squared plus c. Another one. What about the number 5 on its own? Now you have to think a little bit about those two special cases that we talked about when we were doing differentiation. What expression would differentiate to give you an answer of 5? Okay, good. And the answer to that would be 5x plus c. When you differentiate 5x, it takes you back to 5. So let's just, before I reveal the last one, I think there's one more on this screen. Let's have a little think about what the rules are that we have used to get our integrals. So the rule is that I have raised the power by 1, so x squared has become x cubed, x4 has become x5, x1 has become x squared, and in the last one, x0, remember, so x to the power of 0 has become x to the power of 1. So the first thing I do when I'm integrating is raise the power by 1, and then secondly, I divide through by that new power. So in that first one, I raise the power by 1 to give me 3x cubed, and then I've divided through by the new power of 3 to get x cubed. In the second one, I've raised the power by 1 to give me 10x5, and then I've divided through by that new power of 5 to give 2x to the power of 5, and the same rules apply for numbers 3 and number 4. So if I ask you now to finish these off by integrating using that rule, this final expression, what would be the integral of 4x squared plus 5x? Okay, so I'm not having to use trial and error now. I'm going to use that method that I've just looked at. So the first term will be 4x cubed divided by 3, and the second term will be 5x squared divided by 2. And rather than write that in any form of decimal, I've left those as fractions, which you could simplify if needs be, but obviously in this case there is no need. And don't forget the plus c. Okay, good. So well done if you're now understanding that process of integration. We will now write those rules down in our notebooks. So this can all be written down in your notebooks, please. So in the same way as we had a differentiating x to the power of n slide when we were differentiating, we've also got an integrating x to the power of n slide now that we're integrating. So here is my expression ax to the power of n what would happen if I integrate with respect to x, I will get the following. So I've raised the power by 1, and then I've divided through by the new power. And don't forget the plus c. If I have a number on its own, like the integral of 5, integral of 6, integral of -2, then as we've just seen on the previous slide, we will end up with ax plus c. And that's it. So only 2 rules for integration, unlike the 4 that we had for differentiation. Right, so let's have a look at a few examples of questions that we might get in these early stages. So please write this down. You can call it example number 1, and our job is to integrate this expression here with respect to x. Now, the reason why we have chosen this one to use as our first example is because we find that some students think that they can integrate this expression by integrating the x and then integrating the bracket and then multiplying the two together, and that simply does not work. So what we have to do in this case is, first of all, we need to multiply out the bracket. So our first job is to do that little expansion to give us the integral of x5 minus 5x with respect to x. And at that point, I can now use those skills that we've seen for the first few slides to get our final answer. Now, before I give that final answer, I just also want to stress at this point in time how important the notation is. Please use the correct notation for the question, and then please use the correct notation for the answer. Okay, because examiners or markers will be looking out for that notation, and if it's not used correctly, they will penalise you marks for it. So what happens if I integrate each of these two terms? Well, using this rule of integration that we just wrote down in our notebooks, we will end up with 2 separate integrals, as you're seeing here. And the first one will give me x to the power of 6 over 6. The second one will give me minus 5x squared over 2. And then don't forget the plus c as our constant of integration. Here is example number 2, so please write this one down in your notebook as well and label it example 2. And the reason why I've chosen this one is, again, because we can't just integrate the numerator and then integrate the denominator separately and divide one by the other. That doesn't work. So I am going to integrate this expression by simplifying it first and then integrating the result. So we need to use a few skills from the start of the year in order to do that. So first of all, I am going to write my expression as x to the half times x to the power of minus 3. Or I don't have to write it as a multiplication. I can do x to the half divided by x to the power of 3 and take the powers away instead. That's completely up to you. But I've chosen the negative power idea and chosen to do multiplication, but that's not the only way of doing it. But whichever way you choose, you should end up with an answer of x to the minus 5 over 2. Better to leave it as an improper fraction than change it into a decimal. So my new question has therefore become the integral of x to the power of minus 5 over 2 with respect to x. Notice how I'm using the correct notation throughout the question. So using the laws of integration, the rule of integration, I am raising the power by 1. So x to the power of minus 5 over 2 becomes x to the power of minus 3 over 2, and then I'm dividing through by that new power. Now, yes, it does look a bit scruffy, but we can tidy that up afterwards. It's better to have it written in its raw form first before I try and simplify it and potentially make a mistake by trying to do too much all at once. I've also got the plus c, of course, which I keep mentioning because it's important that we include it. So how do I go about simplifying this expression? I mean, I've answered the question. I have an answer. There's nothing wrong with this answer. It just needs to be tidied up. So we learn at school that dividing by minus 3 over 2 is the same as multiplying by 2 over minus 3. So that's the first thing that I'm going to do to simplify this expression, which I've done here. So that's looking better. And again, this is a perfectly acceptable answer. If I was having to sub in a value of x, I probably wouldn't bother doing all of this simplifying, but I need to because I don't have that value of x. So the last thing I'm going to do is to get rid of this negative power. And we learnt in the first term that when we have a negative power, it can go onto the bottom of the fraction, the reciprocal. And again, this looks even better than it did before, but there's one final step that I'm gonna put in, and that is a power of 3 over 2 represents the cube of x and then square rooted. Remember, the top number of the fraction represents the power, and the bottom number of the fraction represents the root. So my final answer will be this, which is the best looking form for the answer that I can give. But most of the second part of this question is all about that all-important algebra manipulation that we did a lot of practice on in term 1. Good, so plenty to practice there. You know, we can't practice this enough, not only because of the integration, but also because of that all-important manipulation of algebra. Sometimes we have to do something to the expression first before we integrate, and sometimes we have to do something to the expression after we've integrated, and both of those skills is really important on this course. So have a go at these two exercises. Any problems, get in touch with your class teacher, and when you're ready, I will see you on the next slide. Good. So one last example, please, for your notebooks. Even though it doesn't say notebooks, I think that this is a really good question to have in your notebooks, please. We will call it example 3. So this is more like a typical exam question that you might get on an assessment or in an exam. And our job is to find the equation of the curve. And in order to find the equation of the curve, I have 2 facts. The first fact is that I know what the gradient function is. So already we need to start thinking about how you can get back to the original curve equation based on the gradient function. And secondly, I am told a point that the curve passes through. So how can we use these 2 facts in order to find the original equation? Well, the first fact that we will concentrate on is the gradient function. So in order to get back to the original, y equals, notice how I'm using correct notation here, y equals the integral of the gradient function with respect to x will take me back to the original y equals equation. So I've got all the skills I need to be able to do that. So 4 would integrate to 4x. We could write, and I would be writing minus 6 over x to the power of 4. I would be writing that as minus 6x to the minus 4. And then when I raise the power by 1 and then divide through the new power, it will give me 2x to the minus 3. And 2x to the minus 3 can be written as 2 over x cubed. So please spend a little bit of time making sure that you understand why the integral of this gradient function turns out to be this equation here. And let's not forget, again, the plus c needs to go on the end. Now, more importantly than any other question that we've seen so far is the need to have that plus c, because your job now is not to leave it as plus c, but to find that actual constant of integration. How am I going to do that? Well, I'm going to do it because I know a point that the curve passes through. And that point that the curve passes through has an x value of 2 and it has a y value of 6. So I can substitute those 2 values into my equation, and that will allow me to find the value of c. So this is a classic exam question because it forces you into having to state the plus c and then find it. So here is my equation that I have so far. Here is me replacing those values of y and x, and if I use my calculator I will find that c is minus 9/4, and so my final answer is y equals 4x plus 2/x cubed minus 9/4. And this final exercise will practice that skill, a really good exercise to make sure you understand the importance of the constant of integration. So have a go, ask your teacher if there's any problems, use the answers in the back of the textbook obviously to guide you as to whether you are going right or wrong. And that completes our basic integration presentation, and I will see you next time. Thank you very much for listening.